Welcome back to Bite-Sized Breakthroughs, the podcast where we break down cutting-edge research in the world of data and technology. Today, we're diving into a fascinating paper from LinkedIn that tackles a critical challenge in recommendation systems, efficiently finding the most relevant content for users. Joining me is Dr. Paige Turner, lead researcher on this project, and Prof. Wid Spectrum, a renowned expert in information retrieval.
Thank you, Alex. It's great to be here. This paper presents LiNR, a large-scale GPU-based retrieval system built for LinkedIn's recommendation engine. We're excited about its potential to transform how we connect users with the content they're most likely to engage with.
It's an exciting topic, Paige. Before we get into the specifics of LiNR, let's establish some context. Professor Spectrum, could you tell us about the challenges faced by traditional recommendation systems and the evolution of retrieval techniques?
Certainly, Alex. Traditional recommender systems often rely on a two-step process: retrieval followed by ranking. Retrieval focuses on finding potential candidates based on user preferences and item characteristics, while ranking assigns scores to these candidates to determine their relevance. The challenge has always been to efficiently retrieve a set of good candidates that represent diverse interests while balancing the trade-off between speed and quality.
That's a great overview, Professor. So how does embedding-based retrieval, EBR, fit into this picture?
EBR, Alex, represents a significant leap forward. It uses machine learning to create numerical representations called embeddings for both users and items. These embeddings capture the underlying semantics and relationships, allowing us to compare users and items in a vector space. The closest items to a user's embedding are then considered the most relevant.
So instead of using keywords or explicit categories, we're using these numerical vectors to understand similarity. That sounds like a more sophisticated way of finding relevant content.
Exactly, Alex. EBR has revolutionized the field, but it still faces challenges. Traditional EBR systems often rely on approximate nearest neighbor search, ANN, algorithms. These algorithms are efficient for large-scale retrieval, but can sometimes compromise accuracy and struggle to handle attribute-based filtering, which is essential for many recommendation scenarios.
Okay, so we have this powerful tool, EBR, but it's not perfect. That's where LiNR comes in. Paige, can you tell us about LiNR's key contributions and innovations?
Certainly, Alex. LiNR takes a different approach to EBR. It's a model-based system, meaning we use a deep neural network to learn the relationships between users and items directly. This allows us to perform exhaustive search with attribute-based pre-filtering, which means we filter out irrelevant items before even calculating similarities. That's a big difference from traditional EBR systems that often rely on post-filtering, which can lead to inaccurate results.
That's intriguing, Paige. So instead of relying on approximations or post-filtering, LiNR is essentially learning how to retrieve the most relevant content from the start. But how does it achieve this exhaustive search with pre-filtering? Could you walk us through the methodology?
Sure, Alex. LiNR implements two main variants of this exhaustive search with attribute-based matching, ABM, KNN with similarity masking, and KNN with explicit pre-filtering.
Let's break down the first one, KNN with similarity masking.
Okay, Alex. In this approach, we first calculate the similarity between the user's embedding and all item embeddings. This gives us a similarity vector that reflects how similar each item is to the user. Next, we use attribute-based clauses to create 0-to-1 mask vectors. These masks indicate whether an item meets the specific criteria specified in the clause. For example, we might have a clause for location or industry. If an item matches the clause's attributes, we'll have a 1 in the corresponding position of the mask vector. We then multiply the similarity vector with these mask vectors, essentially zeroing out the similarity scores of items that don't meet the criteria. This filtering process ensures that only relevant items are considered for the top K selection.
That's an elegant approach, Paige. So you're essentially using these mask vectors to mask out the irrelevant items before you even begin selecting the top K candidates. That must significantly improve the accuracy of the retrieval process.
Exactly, Alex. The second variant, KNN with explicit pre-filtering, takes this a step further. Here, we slice the item embedding matrix based on the attribute clauses before performing similarity calculations. This pre-filtering step significantly reduces the computational overhead, especially when the filters result in a smaller set of candidate items.
That makes sense, Paige. So LiNR's approach to attribute-based pre-filtering is a major departure from traditional EBR systems that often rely on post-filtering. Professor Spectrum, what do you make of this shift from post-filtering to pre-filtering?
It's a significant development, Alex. Traditional post-filtering can lead to wasted candidate slots and a reduction in retrieval quality. By incorporating pre-filtering, LNR ensures that only relevant items are considered, leading to more accurate and efficient retrieval. This is a crucial step towards building truly effective recommendation systems that can cater to specific user needs.
That's a great point, Professor. So LiNR is not just about finding the nearest neighbors, but also about ensuring that those neighbors are the most relevant based on specific attributes. Now, Paige, LiNR also addresses the challenge of handling large-scale data. Can you tell us about the quantization techniques used in the paper?
Certainly, Alex. One of the major challenges in large-scale retrieval is memory consumption. We're dealing with billions of items and their corresponding embeddings, which can quickly strain GPU memory. To tackle this, LNR employs a quantization technique called sign 1 permutation 1 random projection, sign OP or RP. This method allows us to compress embeddings to 1 bit, significantly reducing the memory footprint.
So, instead of storing each dimension of the embedding with a full precision floating point number, we're essentially using a single bit to represent it. How does that impact the accuracy of the retrieval process?
That's a great question, Alex. It's a trade-off. While compression reduces memory consumption, it can potentially affect the accuracy of similarity calculations. However, SinoPOR-P is designed to minimize this impact. It combines a random projection with a bitwise matching approach to approximate the cosine similarity between quantized embeddings. This allows us to perform fast retrieval with minimal loss in accuracy.
That's fascinating, Paige. So LENR is essentially balancing the need for speed and efficiency with the need for accuracy, using quantization to manage memory while maintaining reasonable performance. Now let's talk about LENR's impact. You mentioned that it's been deployed in LinkedIn's production system for out-of-network OON recommendations. Can you tell us more about the A/B testing results?
Of course, Alex. We conducted A/B testing to compare LANR's performance against our existing FIS-based retrieval system. The results were significant. LANR led to a 7% increase in total professional interactions, a 3% increase in daily unique professional users, and a 5% increase in feed update viewers with 30-plus seconds dwell time. We also observed a 20% decrease in the skipped update rate, indicating that users were spending more time engaging with the content recommended by LENR.
Wow, those are impressive results, Paige. It seems like LINR is not only more efficient, but also more effective at connecting users with relevant content. Professor Spectrum, how do you see LINR's performance in the context of other retrieval systems?
LANR's performance is remarkable, Alex. It outperforms both traditional FIS-based systems and the baseline dot product EBR. This highlights the power of model-based retrieval, particularly when combined with techniques like attribute-based pre-filtering and quantization. It's clear that LANR is pushing the boundaries of what's possible in large-scale recommender systems.
It's certainly a game changer. Paige, before we wrap up, let's discuss the limitations and future directions. What are some of the areas where LINR could be improved or extended?
You're right, Alex. While LANR has shown impressive results, there's always room for improvement. One limitation is the custom CUDA implementation for pre-filtering. While effective, it requires significant effort for each new architecture, potentially slowing down model development and deployment. We're exploring more generalizable pre-filtering solutions that can be readily integrated with different similarity measures and operations. Another area for future research is extending LANR's capabilities to handle diverse retrieval scenarios, such as multimodal retrieval involving text, images, and video content. We're also interested in exploring the potential of using generative retrieval techniques in LINR, leveraging transformer-based models to generate semantic structures for retrieval. This could further enhance the efficiency and accuracy of LINR, especially for large-scale datasets.
Those are exciting directions, Paige. Professor Spectrum, What are your thoughts on LiNR's broader impact and potential applications beyond LinkedIn?
LINR's impact is far reaching, Alex. Its core concepts and techniques can be applied to a wide range of recommendation systems, including those used in e commerce, news aggregation, and music streaming. Its ability to handle large scale datasets with high throughput also makes it suitable for applications like search engines, where efficient retrieval of relevant information is crucial. I believe LINR's live updated model based indexing can be especially beneficial for systems dealing with dynamic content such as social media feeds and news websites.
That's a great perspective, Professor. It seems like LINR is not just a solution for LinkedIn, but a potential paradigm shift for the entire field of information retrieval.
Indeed, Alex. LINR demonstrates the power of integrating deep learning techniques into recommendation systems. By leveraging GPU capabilities and differentiable models, LINR has successfully addressed several challenges faced by traditional retrieval systems, setting a new standard for accuracy, efficiency, and scalability. It's a testament to the transformative potential of machine learning in this field.
That's a great way to sum it up, Professor. Thank you both for this insightful discussion. Paige and Professor Spectrum, it's been a pleasure having you on the show.
Thank you for having us, Alex. My pleasure, Alex. It was a fascinating discussion.
And to our listeners, remember to check out the original paper on our website for further details and analysis. And be sure to join us next time for another bite-sized breakthrough.